Okay, thank you very much. I want to thank the organizers for inviting me. I also deeply regret that I could not attend the conference since the beginning, and but I'm really happy to be here. And I want to thank Damien, because when I arrived to Lyon at the ENS, I really felt really welcomed in the team, and it's mainly thanks to Damien. So, okay. So today I will be talking about strongly ergodic equivalence relations and full factors. So I'm more of a Neumann algebra guy, but I'm also interested in the relations with orbit equivalence theory and equivalence relations. And so the goal of my talk is to try to explain some analogies between the two theories, and mainly around strong ergodicity. Okay. So first, the general setting. Let me just recall definitions. So in my talk, when I say equivalence relation, it will always mean countable, Borel, and non-singular equivalence relation on standard probability space. Okay, so I think here I don't need to recall these adjectives, maybe just here because this is a bit not usual for everyone, but you can really think of this as the orbit equivalence relation of some group action of some countable group gamma, countable group action, by non-singular automorphisms. So this means that when you push forward the measure by an element of the group, you don't get the same measure, in which case it will be a probability measure preserving action, but you only get an equivalent measure. So why do we need to bother about non-singular equivalence relations? Well, sometimes you want to, but sometimes you also need to. And what is nice for me today is that I don't have really to give strong motivations for this, because you have a talk this afternoon by Antoine, who will give you a good motivation for studying non-singular equivalence relations. So, motivation. Let's see. So. Oh, I didn't check. Okay, so is it this afternoon also? Yes? No?
It was on Tuesday and it also...
That's why I should have come since the beginning. Yeah, but it's my bad. Okay, okay. Okay. But some of the things I will say will be also about PMP, probability measure preserving actions. Okay. Now I have to define also for factors. So here, a factor. So first, for Neumann algebra, it will always be for Neumann algebra on a separable Hilbert space. Weakly closed, self-adjoint, stable by adjoint. unital subalgebra of B of H, where H is a separable Hilbert space. And as probably many of you know, for every equivalence relation on a probability space X mu, there is a way to construct a von Neumann algebra that usually denote like this on some Hilbert space that with respect to some measure, but it's not the measure we start with here. It's the, I will come back to this later anyway. It's a von Neumann algebra on some Hilbert space, which contains a copy of the L infinity space of your probability space, but it also contains a copy of the full group of R. So this is a group, and it is contained into this von Neumann algebra, and it's represented by unitaries, unitary operators. Unitary operators that normalize this abelian subalgebra and act like the full group of the equivalence relation acts on the probability space. Okay, so this is some standard construction. I don't need to really get in the technical details of this. So usually there are very strong analogies between these two words, and usually you have properties that go from one way to the other. Sometimes it goes, you have really, you get both directions. Sometimes the analogy is a bit imperfect. So for example, we know that R is ergodic if and only if this von Neumann algebra is a factor. And this means that the center of the algebra is the smallest possible. It consists only of scalars. Okay? Okay. So now in this talk, I'm interested into strong ergodicity. So let me record the definition here. So R is strongly ergodic. Yes?
Any R here is just the cross product?
So yes, when R is, yeah, I should say here that if R is the orbit equivalence relation of some free action of some countable group gamma, then the von Neumann algebra state of the equivalence relation is just the cross product by the group. But this is only true when the action is free. Okay? So there are different ways to define strong ergodicity. There is the most natural one, I think, that says that if for every sequence of measurable subsets such of measurable subsets or Borel subsets of X, the space on which R acts, such that it is almost invariant. What does this mean? It means that when you look at this metric difference between AN and some image of AN by an element of the full group of the equivalence relation, this goes to 0 for every theta in the full group. So if your equivalence relation is generated by some group gamma, you only have to check this for elements of the group gamma. If you have a sequence of almost invariant subsets, then asymptotically they must be trivial. We have mu of AN we have that this goes to 0. So this means that asymptotically mu n is either close to 0 or close to 1. Okay? So it's an asymptotic version of ergodicity, stronger than ergodicity. And there is another way to look at this, to characterize strong ergodicity by looking at the cohomology. So for this, I need to recall what the cohomology is. So a cocycle C for an equivalence relation with values in some, you can put any locally compact group, but here I'm using just the torus, the circle group, is a Borel map that is a morphism in the groupoid sense, such that for whenever okay. Once again, if R is the orbit equivalence relation of some group action, then this is just a cocycle for group action that you probably more familiar with. Okay, so this is a cocycle, and a trivial way to get a cocycle is to look at coboundaries. C is a coboundary. If there exists some U so here I'm looking at everything modulo null sets. I'm ignoring null sets. If there exists some map in the torus from the space X such that for all xy in R. Here I should put for almost every xy in R. Okay? So this is a trivial way to get cocycles. Yes?
To be one-dimensional?
Yes, it's a one-dimensional here. But you really can put the same definition for any locally compact group, and then you just have to put here like this. You can really put any locally compact group. Okay, and so why I'm talking about cohomology? Because you have the following, so we denote the coboundaries by so this is a subgroup of the group of all cocycles, one cocycles, and you see on this group you have a natural Polish topology. It's a Polish group because it's really a closed subset of all is closed in equivalence classes of all measurable maps from the equivalence relation into the torus. So this is a closed subgroup. It's a Polish group. So you have a natural topology on it. And the proposition R is strongly ergodic if and only if is closed if this group of co-boundaries is closed in the group of all one cocycles. So, in fact, this is also equivalent to saying, because when you have, because we are dealing here with Polish groups, we have a co-boundary map that goes from this group into the group of co-boundaries. And this map is not injective because you have the constant functions here. But if you mod out by the constant functions and R is ergodic, then this map is an injective group morphism. It is continuous. And if this one is Polish, when you have a measurable continuous bijection between two Polish groups, so it must be a homeomorphism. So saying that R is strongly ergodic is also equivalent to saying that this map is a homeomorphism. And now you can see the relation with strong ergodicity, because this tells you that if you have a set of unitaries like this, of maps like this, such that the co-boundary converges to the identity, becomes more and more trivial, it means that you must be more and more invariant by the full group of the equivalence relation. So you have an almost invariant sequence, and strong ergodicity tells you that it basically means it must be asymptotically trivial. So it is asymptotically in the kernel of this map. So it's another way of saying that this map is a homeomorphism. So this is just technical detail, but it tells you just gives you a hint of why we have this equivalence here. Okay, so I need to use that actually, right? The buttons, okay. Okay. Now, yes?
You can replace the torus with any compact?
No, we really need to use the torus here. Not any, for sure, not every compact group. For example, you can use. I mean, you need some condition, right? It's not. You cannot use trivial groups. You cannot use finite groups. You cannot. So, I mean, the reason that you have relation here is that from a subset here, you can build a map like this by taking an minus the indicator function minus the indicator function of the complementary, and then you really get a reformulation of this. Okay, but certainly there are some class of groups. I can't tell you what is the exact condition you need, but anyway. So, okay, now I have to explain what is the second part of the title of my talk, full factors. And now you will see that from this point of view, the analogy will be very clear. So this is definition that was first given by Kohn. A factor M is full if the group of inner automorphisms. So this is the group of all automorphisms that send an element of the algebra of the factor m to its conjugate by a unitary u. U is a unitary in M. So this is a group of automorphisms of M, and it is contained into the group of all automorphisms of M. And we want this to be closed. So in this analogy, the group of inner automorphism plays the role of coboundaries, and this one plays the role of cocycles and so on. Here on the automorphism group of M, you have a natural Polish topology, which is the set of pointwise convergence on normal states, okay? So really the fullness is somehow the analog of strong ergodicity, but for factors. But we don't have equivalence, so here. Okay. So saying that the factor is full implies that R is strongly ergodic, but the other way around is not always true, but it is true for some equivalence relations, for example, for orbit equivalence relations of actions of free groups or hyperbolic groups. Of actions of free groups. Sorry? Free actions, sorry. Free actions of free groups.
So what are the counterexamples?
Sorry?
What are the counterexamples?
Well, basically the problem is that, so I can't like this give you, so what's happening is that for free groups, these free groups themselves, they are non-inner amenable. So this means that the problem, if you want, is that strong ergodicity, it only tells you what happens in the abelian subalgebra of L infinity of x mu. It does not tell you anything about the unitaries that can live in the whole von Neumann algebra. It's only about those who live in the abelian subalgebra. So you lose some information, and then for some groups you can cook some counterexamples. It's not something difficult, but I can't give you like something like this right now from out of my head. But it's not for some class of groups you cannot have this because they have like some inner amenability or some stronger properties that will tell you. That will property T groups. It will. No, I mean in the PMP case, non-inner amenability is enough. So property T is in particular will implies this, but in the type 3 situation, it's more delicate. You really need something about by exactness or things like that. So anyway, but in the PMP case, really non-inner amenability is enough.
Is it equivalent in the PMP case?
No, you cannot get an equivalence. No. I don't know of any if and only if statement here for these kind of things. It's always, you have always sufficient condition to go like this, but no, not an if and only if condition. So just how much time I have, Eric, here? Okay. Okay, so what I wanted to say now is give you an example of a theorem on equivalence relations that has been proved first for factors, for full factors, and then it was generalized to strongly ergodic equivalence relations. So let me first, for this, give you some. So give you the theorem first on full factors. For now, I will focus on 2-1 factors. So this is a theorem that it's a very important theorem, even in the classification of injective factors. It was an important step in Kahn's work. What Kahn proved is that, so let M be a 2-1 factor, then M is full. By the way, so this is by definition somehow equivalent to saying that M does not have property gamma, for those who know about this. If and only if when you look at the representation of the unitary group of M on the L2 space of M with respect to its canonical trace, this representation has spectral gap. If you want, if you remove here the constant, so you look at really the Koopman representation, remove the constants, this representation has no almost invariant vectors. So saying that M is a factor tells you that this has no invariant vectors. But here, the spectral gap condition tells you that it has no almost invariant vectors. And this is equivalent to saying that M is full. So this is a theorem because there is one direction that is easy. If you have this spectral gap condition, then you get fullness. But the other way around, it's much more surprising and much more difficult. And if you want to think about this, you have to think at the analogy with the strong ergodicity and spectral gap for probability measure preserving action. If an action has spectral gap, its Koopman representation has spectral gap, then it must be strongly ergodic. But the other way around it's not true. Okay? So here, there exists PMP actions such that are strongly ergodic but the Koopman representation when you look at the unitary representation you get from gamma on L2 of X, this one has almost invariant vectors. Sorry? Yes, so that's the theorem now. It shows the difference between this group action case and when you go to the full group. So this is something now that we proved with Cyril and myself and Peter Verrat. It was in 2016. And it's really by analogy with Cohn's theorem now, is that let R be a PMP equivalence relation. Then R is strongly ergodic. If and only if the Koopman representation of the full group of R has spectral gap. So this means that if you have an action like this that is strongly ergodic, strong ergodicity is really a property of the equivalence relation. But you can have two groups that generate the same equivalence relation. They are both strongly ergodic, but one has spectral gap and the other one doesn't. Okay? Or if you want, if we have an action like this, you can always find some group in the full group that has spectral gap, but you cannot really get it for gamma itself. And
one should say that the counterexample of design are not easy. This is the whole notion of strongly action.
yeah. So basically, what would it mean to have there exists some finite set in gamma and some constant such that you have an inequality like this. So you see, this is really equivalent to saying that you have a spectral gap. And this implies the strong ergodicity here, but this is much stronger. This is really give you a uniform bound, and you can really, for example, this property strong ergodicity does not tell you anything about a subset that has very small measure. Because if you have a sequence of subsets AN that are smaller and smaller, well, this condition is trivially verified. They tend to converge to 0. But here you get really an inequality. So it tells you that if this is small, then you have really a control on how small A is. Okay, so it really gives you uniform control. It's much stronger. And basically, if you want to construct counterexamples, you need to construct actions where you can build somehow cook actions where you have like very small, very tiny, almost invariant subsets. In the sense that this is much smaller than the size of A. But so it's not so easy to cook or to describe. Yeah.
But if you have such an inequality for subsets, then they actually has spectral gap.
Yes, this is equivalent to saying that pi has spectral gap.
This linear inequality is equivalent to spectral gap.
This inequality is equivalent to spectral gap. Because once you have this for all measurable subsets, you can deduce something about all functions, and then you really write it in a spectral way in the Hilbert space, using the L2 norm.
So in your theorem on the left,
Yes.
the weakness for the spectrum, you have to solve the finite set?
Yeah, it's also finite set. Yes, it's also finite set. You have so a finitely generated group that has spectral gap. So the point is that if you want to construct the spectral gap, you need to construct some finite set for which you have this, but you cannot construct it in gamma itself. You really have to do some kind of patching, cutting and pasting some elements of the group, so building some elements of the full group, to get something that has spectral gap. And it's really done by some like incremental patching technique. So you use some kind of maximality argument to construct like this. So this gives you, I mean, idea that somehow you need to work to get this spectral gap condition. And the proof, actually, even in Kahn's theorem, this one, he also used a kind of incremental patching thing here. He will construct unitaries here, but patching them using small projections in the von Neumann algebra. Okay? So I want to give you some applications of this. So there are a lot of applications of this in the von Neumann algebra theory, but I want to give you one that's also meaningful for equivalence relations. And this is an application to show that some what we call skew product actions are ergodic. So the example is this one. So let C be a cocycle for your equivalence relation with values in a group G, locally compact and abelian. You can construct what we call an equivalence, a skew product equivalence relation. So if this one is on x mu, this one will be on x times g with the product measure. And you will say that xj is equivalent to yh if x is equivalent to y in R and C of xy is gh minus 1. Okay? So this defines an equivalence relation on the skew product here. And it's usually difficult to determine when such a cross product action is ergodic. This skew product action really does not depend, it only depends on the cohomology class of C. So if C is a co-boundary, you really get something that is not ergodic, because here you can replace C by a trivial cocycle, and you are just looking at R times the trivial equivalence relation here. But if you have a non-trivial cocycle, this can be ergodic, and it's usually not so easy to determine when it is ergodic. But in this situation, so when R is strongly ergodic, you have a nice criterion. So for this, I need to define or maybe I should write it like this. So is ergodic if and only if for every character on J. Okay, so this tells you that if you want to check that this equivalence relation is ergodic, it's enough to check this to check that this condition, that this cocycle is not a co-boundary for every character on the dual group of G. So this is somehow a kind of algebraic criterion that you can check very concretely in situations. R is strongly ergodic, sorry, here. Super. So here, R is strongly ergodic. It's really essential that R is strongly ergodic. Yes, this is also true for non-singular, because we have an adaptation of this kind of theorems for the non-singular case. So once again, so to have an idea that this is not true in general if you don't have the strong ergodicity assumption, once again, in Antoine's talk this afternoon, he will talk a lot about type 3-0 equivalence relations. And for this kind of equivalence relation, you can look at the Maharam extension, where G is really a group of positive real numbers, and C is the Radon-Nikodym cocycle. And for some type 3-0 equivalence relations, this condition will be satisfied. Okay? This will always be, this can be non-trivial for every character on R, and yet this extension will not be ergodic, okay? This will be ergodic for the Maharam extension if and only if the action is of type 3-1, but there are actions type 3-0 equivalence relation for which this is not ergodic by definition, but this is always satisfied. But precisely type 3-0 equivalence relations are never strongly ergodic. So this means, so this is something that I like to call the Wikipedia definition of Krieger type, because there is a mistake on the Wikipedia page. So if you look at the Radon-Nikodym cocycle for an equivalence relation, you can look at the map sigma mu. So let's call it like this. So this depends on the measure mu you choose, but the cohomology class does not depend on mu. You can look at sigma mu, which goes from R into the co-boundaries, which sends T to the Radon-Nikodym cocycle and you take, so, well, if I put it like this depends on mu, but if I look at this map, now I take the cohomology classes. This does not depend on mu. So this is a canonical continuous one-parameter group that goes from R into this cohomology group. And in Wikipedia, they say R is type 3-1 if and only if sigma R is injective. But this is not true in general. It's only true if R is strongly ergodic. If R is strongly ergodic, then if this map is injective, it is 3-1 because of this theorem. And if it is periodic, then it is 3 lambda with a lambda corresponding to the period. But there are cases in the non-strongly ergodic cases where this can be type 3-0, even if this map is injective. And by analogy for factors, for factor m, we have for every faithful state phi, we have a map which we call the modular flow that goes from R to the automorphism group of M, and which gives you a canonical map. This is by a theorem of Kohn, that when you look at it on the outer automorphism group, this one does not depend on the choice of the state. And once again, if M is a full factor, then you can really check the type by looking at the kernel of this map. If this is injective, then it is 3-1. If it is not injective, then it is 3 lambda for some lambda. Okay. By the way, here we can add here something here. If and only if the map from G hat that sends key to key composed with C is a homeomorphism on its range. Okay, and you have a similar statement here. So this is really, in order to prove this theorem, you really need to use the spectral gap that we have here, okay? Okay, so before, yes? So here the statement is 4-to-1, but actually you have an adaptation of this for general equivalence relation, but it's a bit more complicated to state because the Koopman representation, I mean, the action of the full group on the L2 space, you have to correct with the Radon-Nikodym derivatives, and it complicates things. You don't have really an invariant vector that you can remove, so it's a bit more messy in this case. But still, there is an adaptation of this to the type 3 situation. I have still like less than 10 minutes. So let me just give you some theorem that shows a difference now between the equivalence relation word and the full factor word. So let me maybe erase here. So now I'm interested in what we call almost periodic equivalence relations. So mu, or let's say mu in the measure class of mu, is almost periodic with respect to the equivalence relation R, of course. So the context is that we have an equivalence relation R on our space. If the Radon-Nikodym cocycle takes countable values, countably many values. Up to measure 0 subset. Once again, so this kind of measures, they are really much easier to handle because you really have the Radon-Nikodym cocycles only takes values in a countable subgroup, and they, in Antoine's talk again, you will see that these kind of measures play an important role in their constructions. So you have really an interest in knowing when you have such kind of measures because it's much easier to handle technically. And why this term of almost periodicity? Because this is equivalent to saying that this map that I defined there, sigma mu, that goes from R to this cocycle group, is almost periodic. This means that the closure of its image is compact. Then, if you have this, then this is a compact abelian group that contains a copy of R. So the dual group will be a countable subgroup of the positive real numbers, and it will precisely be the values taken by the Radon-Nikodym cocycle. Okay, so you have this duality thing here. And this implies that this canonical map, now in the strongly ergodic case, is almost periodic. Now it turns out that the converse is true. So if R is strongly ergodic, then you can detect the presence of an almost periodic measure and is almost periodic. Then there exists mu such that sigma mu is almost periodic. Moreover, you can really show that this measure mu is unique, essentially unique, if you require that its period group is the smallest possible. It's the same as the one you get here. So it's really a kind of uniqueness, existence and uniqueness statement. And what is somehow was surprising for me at first was that this does not happen. I mean, there are counterexamples for full factors. So let M be a full factor. No, not it like this. So there exists a full factor M such that sigma M is almost periodic. But M has no almost periodic states. And this can only happen so this is a bit vague here. If the group here gamma that is dual to this compact group or here like this contains non-trivial quadratic, a non-trivial quadratic relation with integral coefficients. So what does this mean? So you have this compact group with a copy of dense one parameter subgroup R. So by duality, you get a subgroup of R. And this condition that you have no quadratic relation, at least in the finitely generated case, it's very easy to explain. So this means for gamma finitely generated by freely generated by some elements, let's say T1 to Tn, that there is no polynomial in x1, xn of homogeneous degree 2, homogeneous polynomial of degree 2. such that P of T1, Tn is 0. There is no non-trivial quadratic relation between this set of real numbers, this kind of discrete spectrum, the dual of this. Okay? So this is kind of an algebraic condition that you get on this group. So this is, of course, typically when you get some group, generically you will have no relations like this. So this is something that's very rare and can give you an abstraction here that comes from cohomological abstractions. So I cannot explain this now. But if you don't have this kind of cohomological abstraction, then you have the same result as here. You really have this if and only if criterion. But sometimes it can fail. Okay? So this is somehow a difference between the equivalence relation word and the full factor word. And the construction of these counterexamples, they really use the analog of the theorem that I erased here, that you use Q product constructions and this ergodicity and strong ergodicity criterion to construct these counterexamples. But you use, of course, the analog for full factors. Okay, so let me stop here. Sorry, this was very vague.